Hello everyone. In this video, we will learn how to build crystal structure using Avogadro software. So before creating the crystal structure, let us have some idea about the basic terminology in the crystallography. So very first, we are going to define the crystal structure. So a space lattice can be converted into a crystal when each lattice point is associated with some physical structure, say an atom or molecule, and this physical structure is called basis. So in this diagram you can see these are the lattice points. When you attach these lattice points with a basis, you will get a crystal structure. Now the very fundamental thing that we have to define is the unit cell. So unit cell is a region of the lattice defined by three vectors a, b and c, which when translated by an integral multiple of these vectors reproduces a similar region of the crystal. So a unit cell can be chosen in infinite number of ways. So in figure you are watching four types of unit cells that was numbered by the 1, 2, 3 and 4. So areas of unit cell 1, 2 and 4 are all equal and each represents a unit primitive cell, and the area of the unit cell third is twice as much and represent a non-primitive unit cell. So what is the primitive and non-primitive? So there are two types of unit cell. First is the primitive unit cell. So unit cell with lattice point density of 1 is called a primitive cell, while if the lattice point is more than 1, then it is known as non-primitive unit cell. This is the diagram showing the coordinate system in crystallography. So we have three mutually perpendicular axes that was given by a, b and c vectors, and we are having three angles alpha, beta and gamma. So angle alpha is forming between the axis b vector and c vector, while beta angle is forming between the a vector and c vector, and the gamma angle is forming between the a vector and b vector. So these are basically known as the lattice parameters. Now come to the point symmetry in crystals. So a symmetry operation is a transformation performed on the body which leaves it unchanged. So there are various types of symmetries. So first is the rotation axis. So regular solid bodies have some axis such that when given a definite rotation about it, the body remains in congruent position. What do you mean by congruent? The position that was originally having by the body. So this rotation axis is called an axis of symmetry. So if rotation through 2 pi by n about an axis brings a figure into congruent position, then axis is called n-fold axis of symmetry. So it is a very good point. Crystal does not show 5-fold or any symmetry axis higher than 6. Now second type of symmetry is basically known as plane of symmetry. So a plane of symmetry, a plane passing through an atom and dividing a crystal into two halves such that one half is the mirror reflection of the other is called the plane of symmetry, and such a plane is represented by a symbol m. So this type of nomenclature will be used when we will see the list of space groups. So in a cubic crystal there are three planes of symmetry parallel to the faces of the cube. You can see in the figure. Third is the center of inversion symmetry. This is such a point in a crystal that if a straight line is drawn from any point on the crystal through this center, and produces an equal distance on the other side of this center, it meets an identical point, then it is known as center of inversion, and it is denoted by 1 bar. Now come to the point, very important point, that is the Bravais lattices. So there is a fixed number of ways for arranging points in space lattice such that all the lattice points have exactly the same surroundings. So each of such arrangements of a space lattice is traditionally called Bravais lattice. Now the important point is that there are 32 different 3-dimensional point groups permissible in a 3-dimensional crystal. The 32 permitted crystal point group require 14 different space lattices or Bravais lattices, and the lattices are grouped into 7 systems according to certain specification about the length of edges and angles between them of a convenient unit cell. So we can define the 7 crystal system. So these are the 7 crystal system: triclinic, monoclinic, orthorhombic, tetragonal, cubic, trigonal, hexagonal. They can be differentiated by the value of the lattice parameters. So in the case of the triclinic, the lattice parameters A, B and C are not equal, and the angle alpha, beta, gamma are not equal and not equal to 90 degree. Such a system is called triclinic system. In the case of monoclinic, the system is defined as A not equals to B not equals to C, but alpha equals to gamma equals to 90 degree but not equals to beta. Like the orthorhombic system, in this case cell parameters A not equals to B not equals to C, but alpha, beta, gamma equals to 90 degree. So orthorhombic cell can be of 4 types: simple, base centered, body centered and face centered. Tetragonal, this crystal system is defined as A equals to B not equals to C and alpha, beta, gamma equals to 90 degree. So the tetragonal cell can be of simple P type or body centered I type. And the most important, that is mostly used, is the cubic system, and the cubic system is defined as A equals to B equals to C, alpha, beta, gamma equals to 90 degree. So the cubic cell is of 3 types: simple cubic, body centered cubic and face centered cubic. Then trigonal and hexagonal. Now, so combination of local point symmetry elements, which include angular rotations, center symmetric inversions and reflection in mirror planes. So total are 32 variants. So with translation symmetry, that are basically 14 Bravais lattices, so provides the overall crystal symmetry in 3D space, and that is described by 230 space groups. So you can define in this by a formula: local symmetry plus translation symmetry equals to spatial symmetry. So total local symmetry points are 32 plus 14 Bravais lattices. They will form overall 230 space groups. So we can see the list of these space groups by clicking on this link. This website has the all 230 space group details, starting from number 1, 2 are for the triclinic, then monoclinic, orthorhombic are numbered from 16 to 74, and in the last you have cubic, and they are numbered from 195 to 230. We can check the one by clicking 2 to 5. So this is the 2 to 5 space group. They have symbols, have the usual meanings. For this you can refer the website. So let us now click on the file option and import crystal. So a dialog box open. So there are a large number of files available. So you can select any one. So I am going to click on the elements. There are various elements: iron, helium. Okay, I am going to select sodium. So the file extension of is the basically CIF. So crystal information file, CIF abbreviated as crystal information file. So select this one and insert. So very first you will see only 2 atoms. It basically shows that this unit cell has overall 2 atoms. So basically this is a body centered unit cell, BCC structure, but here in top corner you are watching there is triclinic. So by default it is taking triclinic. So first we will click on the crystallography, then select the space group and perceive space group. So perceived space group is 229. There are 2 types of convention used in this space group. One is the Hermann-Mauszin symbol and other is the Hall symbol. So perceived space group is 229. So we are going to click on the yes. Now you can see that the lattice type is cubic. So by using the view option, you can click on the crystal view options, and here you can display all atoms images. You can see the cell parameters, so A, B and C. Since it is a cubic structure, so the alpha, beta, gamma is 90 degree and ABC is basically all are equal. A equals to B equals to C. So if I am clicking on this display all atoms images, so it will shows all the atoms of the unit cell. You can rotate this unit cell. Now you can clearly watching that unit cell is basically having a centered atom and all the corners are having 1 atoms. So this is basically the BCC structure. If you want to form the supercell, then you can do this by changing the unit cell repeats from here. So select 2, 2 and 2. So this is the supercell structure. By the navigation tool, you can rotate this and translate. So this is a perfect view of the sodium atom having the structure cubic structure. This is the default view. If you want to see the molecule or this structure along the Miller indices, then you can click on the Miller indices. So change the Miller indices, H equals to 1, K equals to 1 and L equals to 1. So now you are watching this unit cell along the Miller indices HKL 111. Now we can draw a different crystal. So again go to the file menu, import crystal, dialog box is opened. Click on the halides, I am selecting the NaCl molecule. So, insert NaCl. Already cell repeated, so first reduce the number. So, 1, 1 and 1. So, this is the unit cell of the sodium chloride, but still here we are watching that lattice tab is basically showing the triclinic. So, by default it is showing the triclinic. So, we need to click on the crystallography, then space group and perceived space group. So, perceived space group is 225. So, okay, yes. Now, you can see the lattice type is the cubic structure. So, by this way you can construct or build any crystal structure using the already defined CI file in the Avogadro software. Thank you.